Hello, everyone. Thanks for joining. This is the Unlocking the Full Potential of 3D Data webinar. I am your host, Kevin Hoffman. Joining me today, Paul will be here. He's a little bit late, but he is the founder and CEO of Physna. He's been a visionary in this space and is a regular in the national and international news on the revolutionary effects of 3D search and analysis. We also have Andy Lloyd. Andy is our Director of Customer Success. He has 34 years of military experience, mostly in the supply chain and logistics. And last but not least, we have Ralph Mira. He is our Head of Sales Engineering. He is an experienced platform architect with companies like VMware and Pivotal. As far as the agenda, we've allotted 15 minutes today for a high-level demo of Physna, followed by some background on the solution and the typical use cases that we see. And at the end, we'll leave it open for some Q&A with Paul and a call to action. But before we get to that demo, I want to start with that overview. So if you're in manufacturing, 3D data is a critical component to your business, and most products begin their lives as a 3D model. The problem is most technologies are clueless when it comes to understanding 3D models. They rely on metadata like bill of materials, parts, part numbers or SKU numbers. Even in scenarios where you know the metadata you're looking for, it can still be practically impossible to find things. At Physna, we've spent years working with manufacturers across design, supply chain, and procurement to unlock the potential of 3D through precision geometry. So you may ask, how do we do that? Well, we solve these business problems through a geometric lens using math, not just metadata. We have our patented set of algorithms that creates a unique fingerprint-like identifier we call physical DNA, hence the name Physna. So this PNA, this Physna DNA, with hundreds of thousands of data points, allows us to find and compare parts within assemblies and subassemblies that exist within a single model. And once Physna analyzes your PLM libraries, people from across your organization can quickly compare models across suppliers and discover if a part exists, where it fits, and find parts for reuse. We can also classify and categorize parts through the use of AI and ML. Our ability to organize and simplify 3D catalogs allows our customers to focus on innovation instead of recreation. And how exactly do we do that? Well, I'll let Ralph show you. Ralph, over to you.
Thank you, Kevin. I'm going to share my screen over here. Okay. We're going to start quite aptly here. Can you see my screen okay? Yep.
Yes.
Okay. So we're going to start with a 3D object. I'm just using a browser. So that's one of the incredible features about Physna is really we're democratizing access to 3D data. Anybody that has a mouse in a browser can access 3D data as long as they have permissions to do so. In this case here, it's a bolt. I'm a procurement person, for example. The bolt is not in stock, so I'm in trouble. I need to find an alternative, a suitable substitute. Physna's interface allows you to simply click here and say, find matches. And in a matter of seconds, you can see that it found 5 other alternatives. The top one being a 100% match, which makes it very interesting. Even though the name is completely different from what I was looking for initially, it's definitely the same kind of bolt. It's a hex head. I see the diameters, the sizes. And the fact that Physna says it's a 100% match makes it absolutely sure through math that we're dealing with the right answer. I reorganized the titles over here or the headers so you could see that from a procurement perspective, I know that it's available, I know the material, I know where to go get it, and I even have a sense of price. So this allows very quickly for somebody across the company to talk to engineering, discuss again, finding a substitute component to get us out of a bind. Let me just move this over here. So what else can I do with this? Well, let's say somebody is in design engineering and they're in the process of designing an arm wastegate for a turbocharger. Physna can perform the same type of match, but in this case here, a part match. That is something bigger than the original piece. And then I can do this. I can add both these parts to a compare cart and let Physna compare the two so that I can see exactly that the design that I was about to do and complete is already a perfect match with something that exists. In the industry, this happens all the time. Engineers quite often get frustrated not being able to find by searching. And so we facilitate that process significantly. Now, let's say you don't have a 3D part, but you have the part itself, the physical part in your hands. So let's say somebody shipped to you this pneumatic stopper inside a plastic bag. So let's take it and give that picture to Physna and see if Physna can find that object. So here I'm going from 2D, from a picture, and finding a 3D object. Physna found some possible candidates over here. I can visually detect that this is the right answer. And now note that this is actually an assembly, and I can perform a search. And just adjusting the tolerance level over here. Look at how interesting. From a picture, I was able to find the 3D object, and I was even able to find the assembly that holds that object. So quite powerful to go from 2D to 3D and find the objects. Well, let's take it to the next level. Let's say we have a brush cutter like this device over here, and we have a wood chipper like this one here, and I want the intersection of the two. I want to know, what do they share in common? So it's a match report. That's kind of the language we use. Here, if I do the intersection of the brush cutter with the wood chipper, let me change the opacity a little bit, and voila. I just found that they share some bolts over here. They share the carburetor, the spark plug. Really interesting, the inside of this knob, the inside of the handles. And this was really a good find. The threading of these bolts is shared between the two devices. So this is probably a hex head versus a Torx screw, for example. So an opportunity to reduce complexity and reduce costs. So what else can I do? If I don't have a 3D model, perhaps I can get a scan of a model. Like in this case here, this was an impeller obtained from the field using photogrammetry. If I perform a find, again, Physna has this option over here, the scan match, where it lists all the possible kind of similar shapes, similar volume. It's quite complex kind of a query because of the high number of polygons that are involved. But there, I find a match. I find this one here, for example, that is a CAD file. And I can compare the two. So there is the original. I'm comparing it to the reference. And Physna is showing me that there's a problem over here and over here. This is quite useful when you're doing prototyping of additive manufacturing. So you're printing objects and you're quickly comparing them so that you can iterate and get to the right device, or in quality inspection, for example. Okay, so let's go back to that bolt. We found that the bolt had 5 possible substitutes, the top one being the 100% match. But Physna is also telling me that the bolt fits into the turbocharger. So that's something I can show you. I can compare the two. I'm going to open a new tab over here. And what I want to see is the overlay of the turbocharger intersected with the bolt. And I'm going to play with the opacity here a little bit. And look how interesting. There are 8 bolts in that turbocharger. And Physna found each and every one of them starting from the original one. Now there was also this option over here, classification match, and this gets to be quite useful when you're dealing with size variance. So you're dealing with a bolt, but you want perhaps a bolt in the same shape and slightly larger, or something from the family of bolts. You can see that Physna has correctly identified other bolts. Even in this case here, where it has not been confirmed to be a bolt, there's a high level of confidence that it is a bolt. How does that work? Well, as an example, we took the McMaster-Carr catalog, ingested into Physna, and gave it to what we call geometric classification. So by identifying certain examples of what a ball joint rod is, Physna can now make predictions And those predictions are what we see here when we do a classification match. It's checking against the class or the grouping of bolts in the case of the bolt. In this example, ball joints. In this example here, I provided self-leveling mounts, and Physna has learned what a self-leveling mount is. In this example here, sprockets, and then here, hand wheels. So 4 spokes, 3 spokes, 2 spokes. It literally has learned what a hand wheel is and is making good predictions. And that kind of tightens the circle back into being able to find the right object, be it a precise match, be it a part within a part, something that has the same reasonable volume and some of the shape commonalities, or within the family of bolts. So we've attacked the problem of searching from all angles. If you happen to be interested in connecting to Physna and using the functionality, we also have all the documentation available through application programming interfaces. So we've got guides on how to connect and use, and it's quite extensive, the set of APIs that you can call. And I'll kind of leave you with this last example over here. This is a Tesla valve, and I am going to see. I'm going to cut it over here just to show you what it looks like inside. So this again is another feature of the tool. So this is what it looks inside, like inside. If I do a find matches and I lower the percentage match, it says, oh, you found something else similar, but it's a 78% match. Now, if I compare the two side by side, and I'm going to use X-ray, I can see exactly why they're different. So this is something that goes beyond shape search. This is true geometric search, leading you to find similarities or find differences and get yourself out of a bind group potentially. Okay, I will kind of hand it back to Kevin, and so that we can talk about the use cases where this applies. You're muted, Kevin.
There we go. Sorry about that. Thanks, Ralph. Wanted a quick reminder, if you guys have any questions, feel free to put those in the chat. Wanted to go over real quick some use cases and some potential ROI. As the world's only true 3D geometric deep learning solution, our patent algorithms and normalization process have been able to help our customers save millions of dollars through 8 main use cases, and I wanted to go over those with you. So the first big one, and the low-hanging fruit, is called reducing design time and search with reuse. So with an average engineer spending roughly 12 hours a week searching for models, and those same engineers normally giving up after about 15 minutes of searching and opting to design something new, somebody with Physna can find a part in 15 seconds and thus reduce the design time and complexity across the supply chain because they're no longer building parts that have already been built. So that's a big one. The next one is the clean parts inventory. So I'd like to think everybody would agree that a clean and organized 3D catalog enables engineers and designers to focus on innovation instead of recreation. But if you can reduce the number of SKUs by identifying duplicate parts, you're looking at a savings of up to about $28,000 per SKU. So you can see a tremendous amount of ROI just with one SKU. Maintenance optimization. So this is the use case Ralph mentioned when you take out a picture of something. So imagine if you're looking for a needle in a haystack type of part, and what if you can identify that part with just a photo? So here comes Physna. Physna can actually take a photo with photo to 3D technology, can find models from a scan or a photo. This functionality has helped a major automotive manufacturer save hundreds of thousands of dollars by avoiding unplanned downtime by quickly identifying broken parts on an assembly floor and helping them determine if the part can be 3D printed. So pretty unique. We actually just got an Air Force SIBR based on this technology as well that Andy might mention a little later on in the Q&A. The next one is the procurement. We have another customer doing this as well. So with respect to that, we have procurement can improve their quotation analysis time from weeks to hours by using Physna to geometrically search for similar projects in previous quotes. This is a strategic advantage for our customers who bid on work. So again, in many cases, these guys in procurement take weeks on end to actually do a quote. We can make that way more efficient. So inventory rationalization and supply chain optimization have been hot topics in the last few years. Given Phyzna's ability to find alternate parts and suppliers based on their geometry, this can directly impact sourcing by prompting a data-driven review of suppliers and inventory and the development of alternative sources or even the consolidation of sources. So this can help you in that supply chain optimization. And last but not least is this idea of sustainability and carbon footprint, which has been another hot topic. Physna can help you reduce your carbon footprint by supporting an effective reduce, reuse, and recycle strategy by giving you the ability to assign a carbon footprint to your suppliers, thus allowing you to make more informed decisions. So Physna can be used in every phase of your business. So having a clean and organized 3D data that is actionable creates immediate value for everyone in your organization from concept to field repair. So my question for everybody on this call would be, what question can Physna answer for you? And with that, I'm going to throw it over to Andy for some Q&A, and hopefully Paul is able to join us.
Okay, so good afternoon or evening, depending on where you are. So Andy Lloyd, as was introduced earlier. So we're going to start to bring in some questions, and I'm going to ask Ralph, who's just presented, to answer a couple of questions in a moment, and happy to take any more then as they come up. And just to re-emphasize, as Kevin just mentioned, we've just been accepted for a SIBR Phase 2, which is working with the US Air Force and looking at how to manage basically obsolescence and diminishing manufacturing sources and material shortages. And that piece of work is pretty exciting and builds on the industry use cases that Kevin has just talked about. So we now just want to explore some questions that have been coming. Some of them you've seen that have been written online. But the first question that was posed to us a while ago offline, I just want to ask of Ralph Mehra, and that is, Ralph, directly leading on from your presentation, there are companies I know that do say that they can do much of what Physna can do. What differentiates Physna from competitors, and why do you see that makes it uniquely placed to give industry a competitive advantage?
Well, in essence, we cracked the code on how to extract geometry in a mathematical way, in a deterministic way, from 3D files, not just open source files, but files from SO or Siemens or PTC. So we can see across the board what things are common in terms of geometry, and not just at the part level, but at the assembly level, like I demonstrated. So this is a very, very unique feature, right? Being able to find an assembly within another assembly and find other similar objects, or with precision, be able to guarantee that something is 100% match, which for engineers with tolerances becomes a very big issue. So in short, multi-file support, assembly and part search, and true geometry sets us apart from any shapes that go out there.
Okay, Ralph, thank you for that one. And again, happy to take, and I'm seeing some comments in the Q&A, and I'll be picking those up in a moment. A further question I want to put, and maybe towards Kevin, but also Ralph as well. What would you say has really excited customers about the technology that you've shown and how you've demonstrated it? What's really excited them?
I would go with the dedupe. And most people, I think, is the ability to find a part is extremely difficult, and not even knowing how many parts they have that are actual duplications of other parts. So that's been probably the biggest driver, and getting a clean 3D catalog is also a big ask as well. Ralph?
We find a lot of, we get a lot of good results with the photo to 3D. It really kind of shocks people that we're able to do what we can do. And the technology is actually quite straightforward. The system learns by itself, by having the 3D objects, how to visualize it from a picture or 2D perspective. But we don't really have to do anything except load the 3D object, and the system trains itself on how to find it. So it's scalable, it's very efficient, and it opens a whole new kind of space when you have something. This happens all the time at home, right? You have a drawer full of things, you don't even know where they go. Wouldn't it be great if you could just take a picture and it could show you what that component is? So yeah, very, very powerful feature.
So, Ralph, what I might advise there is if you're able to turn your camera off and just reduce your bandwidth slightly, I think some of your sound is a bit intermittent, but your message comes through loud and clear. And it is a particularly important one there in terms of the development of image to 3D and how this system is going to enhance how you can just take a photo and translate that to match to your inventory and your CAD files. So thank you for that answer, Ralph. Is there anything more that you would wish to add to that one, Kevin, based on your experience and feedback from customers?
No, I think Ralph covered it.
Okay. So I'm going to ask Ralph, and we'll just check on your sound. But Ralph, I'd like to just ask you, having been in this industry a long time, question that came into me was, what would you say are the most exciting next steps for Physna's technology?
I guess it's what you mentioned a few minutes ago. The CIBR with the Air Force is going to take us to the million-plus scale. We already handle millions of objects with our public website called things.com. We have about 50 million objects indexed, and a lot of the core technology I demonstrated today is embedded into that website. But being able to actually help our nation with search at the DoD level, I think is kind of tremendous. And then beyond that, the ability to scan a room and be able to identify each and every component that's in that room from a simple scanner, as more and more devices, Samsung, iPhones, LiDAR capability, that's going to open a whole new space. And then ultimately, the AR, MR kind of space is going to kind of open the opportunity as well for business technology to expand itself.
Excellent.
Sorry, I see that I am so late for this thing. I just arrived and was able to get in just now.
Hello, Paul. So we're just going through some questions and answers, and the ones that we've covered that were fed to us were just what differentiated Physna from competitors. And just to you as CEO, is there anything that you would wish to add on that make that to your mind from Phyzna's journey that clearly you've been from the start, you would see as A, exciting, and B, a real market differentiator?
Yeah, I think, well, the way that this company got founded, right, was from patent law, and the bar for that was really high. We had to see not only the parts were identical or similar, but how they're related in every way. And so the tools that we found out there didn't work for that. They weren't even always able to find identical parts. So the process of creating what we have at Physna was a very laborious one. But at the end, now what we have is something where if you take the example I love to use, I'm not sure if this was used before, but if you take a vase and shatter it against the wall, we can literally take those shards of glass and say, this is how you put Humpty Dumpty back together again. We know that these shards belong in this vase and where, no metadata, no bill of material, purely on geometry. So that's something that makes it separate, because Physna is able to treat 3D models just like as if it were text. You wouldn't be surprised if you did a search in a book or a document or on the internet and it found the word or the combination of letters and exactly where they're located. but that was never possible with geometry before. So I would say that what makes Physna unique is not only that it has the ability to do that across all those file types, it has that DNA, if you will, but it also means that but what that means is really just that it's more useful to the across the board. If you're an engineer, that means that you can use it for autofill. If you're in the process of designing something, we can use what you're designing to guess what you're probably going to want at the end and use that for search. If you're in supply chain or in procurement, that means that we can identify alternative components, help you standardize between parts more easily. Again, even when there's no bill of material, file hierarchy, or metadata connecting any of these models. And if you're out in the field, it means that we can actually do things like more accurate image search than anyone else can offer. So we can take a picture from your phone, for instance, and find exactly what that is, and then do geometric search how and where that's used. There's one other capability I think is really key here and important when it comes to what differentiates us. And that is that because we have that capability, there's another layer to what we can do with your data. So, and that comes in the form of machine learning and predictions that is customized to every customer. So on one hand, of course, we can take all the models that you have and label them and classify them and say, this is what this is. But because of that subpart relationship, as long as what you're tracking is objective, and you say some parts you've labeled as prone to breaking or need to be made out of a certain material or with a certain methodology or what have you, as long as it's objective, we can actually forecast that, because we can say, hey, this model contains elements that seem to coincide with, a certain outcome, a certain cost, a certain process, et cetera. And one example I'll give briefly, and then I'll try to end there, is one where a customer sent us examples of shampoo bottles that were breaking with tiny geometric changes. They didn't know why some were fine and some would break in transit. And we uploaded them, the ones that were labeled as bad or breaking, we labeled them, they were uploaded as such. There's like 5 bad ones and 5 good ones. And then with the other models that they sent were not labeled. And it was 100% accurate at guessing which one was going to break and which one wasn't, because it was able to figure out what aspect of that micro change in the geometry actually was causing those shampoo bottles to break. And that was something that was troubling this firm for a really long time. And we were able to solve it within, I think 10, 20 minutes. So that level of depth, I think, is really what sets Physna apart, and what that unlocks is just a significantly more ROI than would be possible in the past.
Andy, you're muted.
Andy, you're on mute.
The age-old on mute. So what I'd like to do just at this stage is just see if there's any questions. We've been picking them up through the Q&A, but to our Deep Tech Showcase people, is it okay if we open up the floor and see if there's any questions people would like to raise their hands?
Absolutely. And I saw there's a few questions that were very interesting that were answered by a bunch of you, but I think it might be worth reading them out loud and answering them also live, so that the rest of the people can also hear the answers. The first question that caught my attention was, can the system be applied for bioorganism 3D digitalization?
Yes, with one caveat though. So Physna, it's a great question actually. Physna has multiple ways of analyzing models, and some of them are deterministic, meaning it's extremely literal, right? If something's identical, it's identical. And some of them are non-deterministic, meaning it's looking for similarity. We would almost consider this to be like true geometry versus appearance. So with biological masses, and I'm not a doctor, but we had some companies come to us and want to see, what we were able to do with them or for them. What we were able to show was like, we were able to identify the classification of what an area was. Like, okay, this is a scan of a lung versus the scan of a kidney, for instance. Now, if you were to give us 2 scans of the same lung, one after another, the deterministic algorithm would say, these are all the changes. And there'd be tons of them because your lung is moving, right? So not be in the exact same position, but enough of it would be consistent that it would still match. The non-deterministic side would say, yes, this definitely, these 2 lungs are similar. Maybe another person, we could say that they also have lungs. We see that that's a pair of lungs, but it's not from the same individual. So it wouldn't be as precise, but it would still be more almost you almost say more accurate. The combination is really cool though, because what we're able to do with bioorganisms and really with any models, the way that again, and I don't understand this area very well, so I might say something that's a little bit off, but my understanding is that when you have a CT scan come in, an MRI scan, anything that's 3-dimensional scan, they generate files and formats just like anything else. And what happens there is the density information, and at least some of these scans, I think with CT scanning, we were able to prove this, that there were density abnormalities in some of these scans that we were able to detect, and they were not visible to the naked eye. And so where I could see that being valuable, and this is what we were approached about, was there are certain types of cancers and abnormalities and illnesses that are present in a way that you could almost feel, like in a density manner. But when you look at the actual scan itself, it doesn't necessarily visually show itself, right? If you're looking at it like slice by slice, the area of like the shade of gray might be the same, right? And so what's unique about the 3D aspect is that we can pick up on, okay, this is a lung and it has a density abnormality. We can correlate that to the likelihood of that being, let's say, a cancerous tissue. We could say, hey, I wouldn't ever say we have the ability to diagnose anything, but we could definitely highlight that and say, hey, we found this area of abnormality here in the scan. A doctor should probably take a really close look at this, or maybe even a biopsy, and say, is that a very early phase of cancer? Now, this is based off of a few very, very, very early, very simple tests. So I'm not saying that Physna is going to save everyone's life. I would love it if it did. But at a theoretical level, that is certainly possible. And to answer the simpler question, yes, it can match between biological things, but of course, because of the fluid nature of them, sometimes the precision will be a little bit different than if it's non-biological.
That's amazing. Definitely, I'm happy someone asked it, because it's definitely a different use case and a different application that might not have come up today, at least. The last question that came through, which Kevin answered, is regarding the business model. Would you like to talk about the business model, what your focus is, who you guys are looking to connect with? So there's many different people on this call today.
Sure. So
Yeah. Oh, go ahead.
Sorry.
Go ahead, Paul.
Oh, okay. Sorry. So the primary business model is so even though we started off in SaaS and we do have a user interface, we've found that the best way to deploy Physna is actually through an API, so that it can work with any existing programs that a company has. So we try to make the billing very simple. So we think of it like a hybrid SaaS PaaS model when it comes to the way that we charge. Typically, there's a flat fee, a certain number of API calls are exceeded, and then it goes to more of a PaaS model that just keeps it simpler, so people know what they're going to spend. Because this is a really new type of technology, and people want to know what's the cost going to be. The nice thing about it though is when it comes to like who do we look for? We look for areas where we can have the most impact, right? So the amazing thing about Physna to me, and again, of course I'm biased, but what really drives me, wakes me up in the morning, is when I see the ROI that we have, the impact that we have on these companies. So if in engineering, we're making engineers faster, better, making better decisions, their work becomes more scalable. You're not needlessly redesigning the same part over again. And because you're not doing that, you're not causing problems downstream for procurement or inventory management, et cetera. I love seeing cases where in procurement or supply chain, we're able to help with the not only reduce the cost so much, but even the improve the resiliency of the supply chain. We can say, hey, you're ordering that same part from dozens of different vendors. You can save a lot of money by consolidating it to the the best offer and getting a bulk deal. And also you'll be more resilient, because if you're ordering from 30 vendors and you only need to order from one, well, now you know that you have 30 options for if any one vendor were to go out, versus you're reliant on 30 different vendors just to operate. So you become exponentially more resilient. And we've definitely seen cases here where there were so many duplicate parts and databases and so many standardization opportunities that within just a few days of people using Physna, we were identified like, hey, you might be wasting like 40% of your procurement budget. That's a huge opportunity in my mind, right? You have a huge opportunity to save. And so I think it'd be really hard to imagine it not paying for itself in those cases. And then lastly, it's flexibility, right? So we really like working with companies. The use case is almost secondary, as long as the functionality is something that we have, and we're not having to build something totally different. One thing I love about is the flexibility that API model gives us. So what we'll see is in some companies, they'll use multiple APIs or the same one for multiple different programs, all the way from improving engineering speed and productivity through to supply chain management, and then using the image recognition capabilities to say, hey, I want to know what this part is, where it goes, what I can do with it, what alternatives exist, even visualize this in augmented reality through my phone, or what have you. That's something that really excites me. Because of that flexibility, though, and because of we're a little bit ahead of our time as far as the core tech is concerned. We do have a lot of demand right now. So one thing that we're, and I don't know if anyone's mentioned this or not, but that we're going to have to impose here relatively soon is that in a few weeks we'll be meeting to decide which partnerships and deals we'll actually take on. We'll have to limit it just because of the amount of resources that we have. We have both a lot going on the API side, the enterprise side, and we also operate the site thangs.com, which has been growing exponentially over the past year. We have 28 times more uploads per week than we had a year ago. We're at 15 million plus models. We should expect to hit 100 million by the end of the year. So that's taking up a lot of resources. And so it's a good problem to have, but it's still a problem. We need to decide what we're going to take on. So companies that have, significant challenges or see significant opportunities, whether they're enterprise companies or tech companies that want to solve a problem similar or different to what we've mentioned, but through the same technology, we would want to ideally hear from them relatively soon, just so that we can make a decision in a few weeks which ones we'll take on. We'll probably limit it to something like 5 different opportunities. So it's a relatively small number, and the further along we are, the better. So I hope that gives a little bit of an answer, but typically the companies we work with, I mean, they're very diverse. They're, a lot of them are in manufacturing and they're industrial companies, but there are companies that are tech companies, and they work in, like AR, VR type spaces that we work with as well. So it has less to do with the type of company and more to do with the impact that we can have, and the magnitude of the problem we can solve, and just their readiness to work with us.
So, Paul, I'm picking up a couple of questions, and I know that this gentleman has been on in previous calls, so he's clearly looking closely at our tech. Matthew Krudican has asked 2 questions. If I can frame the 2, and then do please pick how to answer, and maybe we'll go back to him with more detail. But it's, how efficient is edge processing for terrain matching as well as change detection? How easily can we ingest macro and micro items? And his second question is, what type of physics understanding could this match if one used various types of sensors, i.e. LiDAR, thermal?
Okay, there's a lot in that. So let's start with the first one. So the first one, if I understood correctly, specific to edge computing, so our primary way of computing here, just to keep things simple, is through a single tenant cloud environment that has both the advantage of being able to scale up and down, but it has all the security of being single tenant. So we wouldn't do it on the edge as much, but I know what you're getting at, and there is a way and we have done this in the past in a previous thing that we've built, a program that we built, which would do some of the data generation on the hardware side or the PC side, and then it would share that to the cloud, and then we would get results from there. As far as, if I understood correctly, the first question was about was it about the speed or the compatibility? Andy?
So the question that we've got is, I'll repeat then, is how efficient is edge processing for terrain mapping?
Terrain mapping.
Matching.
Terrain matching. Okay. Well, I mean, so Physna is pretty much agnostic when it comes to the type of data that comes in. As long as it's a 3D format that we support, it won't care if it's terrain data, if it's a 3D model of Pikachu, biomass. It really won't matter. What's going to matter is how much data is it, right? I mean, how much data are we talking about? And then, but at the end of the day, it comes down to how much is being uploaded and then has to be processed. So if it's edge computing, the answer would be, well, if a lot of it's done, a lot of that processing is done on the user side and the hardware side before it goes into the cloud, and it reduces the amount of data either by simplifying or by just what's what I'm looking for. The degradation level is such that it's not sending up something with 1 trillion polygons that's 100,000 or 1 million or whatever. It'll be vastly different than if you were to upload, this really raw data that has exponentially more, let's say, polygons here to keep it simple. It's really hard to give you an example, a simple answer on efficiency, though, because I don't know how much data it would be, right? So I can give you anecdotal information that might be helpful, and Ralph might be able to chime in on this as well. But small, simple models can be uploaded and processed in a matter of seconds. When you get to really large models that contain lots and lots of data, like models, for instance, that contain that are of factories and contain components there, that could take minutes, or if it's large enough and complicated enough, it could even potentially take a couple of hours, if in the extreme cases. But there is, again, because this is cloud-based on our end, we're able to, scale things as necessary. So we could make that an order of magnitude faster. The complicating factor, though, is the edge processing. So the examples I'm giving are, we're getting the raw data without any processing happening in advance. I hope that answered that question. If not, please feel free to correct me on what you actually meant, and I'm happy to try to answer it again. The second one was around the physics that we're able to detect based on LiDAR and thermal. Did I repeat that correctly?
That is correct. Is it able to match if used? Let me read it out. What type of physics understanding could this match if one used various types of sensors, i.e. LiDAR, thermal?
Got it. Okay. So when you say physics understanding, it would be great to understand what you mean by that. Like I'll give you a simple example of kind of how this all works, and maybe this will answer it maybe indirectly, but in a more meaningful way than I can probably ascertain from the question, because I'm not necessarily exactly what you mean. If you have data like a LiDAR scan or any other 3D topology, any 3D information about the model, you can correlate that information with anything that matches it. So if I'm just going to assume that you're still talking about terrain topology. Let's say that you scanned an area once and nothing was built on it, and then you scanned an area again and there was a little house built on it. If you labeled the second one as, scan with house or something like that, and then you scanned another area that was similar maybe, but had a house on it, there's a good chance that it would then predict, hey, even if it's not labeled as having a house, we detected a house, right? And that's because it's objective data and objective geometric data. So what could you do with physics? Well, if there's a correlation between that topography, the geometry of what you're scanning, and the output, whatever that is, as long as that's an objective correlation, in theory, that should be able to be predicted, right? It should not require a whole lot of training data to do it, as long as the data is consistent, right? So if you're using different types of scanning methodologies and getting very different, very different scans of a certain topology, it'll be very hard for it to make those, predictions as accurately as if you're using a consistent methodology. When it comes to things like thermals, what I can say is that, so thermal, and again, I might be wrong, unless that can express itself in a 3-dimensional way. If we just had thermals and it was a 2-dimensional format, like this is the coloration of an area, that probably wouldn't be something we could do anything with on its own without any other accompanying data. But again, any data can be associated, right? So with the geometry. So if you had a LiDAR scan and correlating thermals, and let's say that there was a correlation between the presence of a hill and a certain thermal pattern, right? Then with the API, it would be possible to make an adjustment to where it's not looking for a tag, right? Like a label as far as like a word's concerned, but it was correlating it to a certain thermal output. And then it might be able to predict the thermals on similar geographies later, using probably a vision-based API in conjunction with that. So if that's what you mean, you would be able to make a correlation there. You just have to do a little bit of tweaking.
Paul, thank you very much for a very thorough answer. We are coming close to time. There would be time for one more question if anybody else wishes to raise their hand. And if not, we'll look in a moment to bring this to a close. So Kevin, it is going to be back to you then to produce the call to action.
Is there one of you two, Ralph, or you? Ralph, do you want to talk about the tiny URL?
Yeah, so if you click on this URL, you will be taken to a form where we're allowing you to upload up to 10 objects in 3D so that we can run some simulations for you, find some duplicates, find objects within objects. It's a lot of fun. We never know what we're going to get, but we simply apply Physna to find the correlations and the similarities. So if you click on this URL, it will take you to a form, and then that let's say you uploaded a V6 engine like this one here, and you uploaded several of its components as well. We would be able to show you where they fit, for example. So it's just an idea. If you're curious about the technology, this is something we can definitely help with.
Ralph, would you mind maybe sharing that URL in the live chat or something, just so that people don't have to type it up? Because I don't think there's a way for anyone to click on it as such.
We're happy to share it also in an email. We'll send everyone a recording and you know, as well as your contact info, which was my next point, is that if anyone wants to contact you guys, maybe at this point you guys should put any contact information into the chat, so that everyone can have access to that.
I believe that was just added in response to a question, but
Yes, I've just added to some to come to me through LinkedIn if they can find me, or to come back through DT Showcase in the first instance, and we're very happy to respond very quickly.
Fantastic. I'll share that information as well with the registrants. Anything else that you guys would like to cover before we bring the session to an end?
I might just connect something that Ralph shared with the statement that I made there. One of the reasons that we have this tiny URL link available right now is one of the first questions we normally get from people who are interested in the technology but want to see if it works is like, can you show me it working on, you know, my models or models that I give you? And this is a way to maybe expedite that process, since, as I mentioned, you know, we are kind of getting towards a time in the year where we're going to have to kind of make some decisions. So if this is something where you're like, hey, this might be really interesting, but I want to see what Physna is able to produce with, you know, this group of models here. Again, we won't share with anybody besides you the results, but you know, only share what you feel comfortable sharing. That might be an expedited way to, you know, prove or disprove that there's a fit or that there's not, right, in a quick way. So I would encourage people to use this as a way to test it if you're interested. And by all means, feel free to reach out with any other questions, and we'd be very happy to talk to you.
Fantastic. Thank you very much to everyone at Physna. Thank you for everyone who's still logged on. And yeah, it was fantastic.
Okay, thank you.
Yeah, and have a great day, evening, night, you know, wherever everyone is.
Thank you.